Dear students, welcome to this next video about chapter 3 of the advanced training program for liquefied gas tankers. In this chapter 3 we will discuss the rules and regulations. I will not go through the whole regulation, but I picked some items that from a point of view of the operator of a gas tanker might be of importance. I will not discuss all the requirements that are mentioned in the different regulations about the construction of the vessel. I assume that when you come on board of the ship, the vessel has been constructed and finished. If this is not the case and they send you to a shipyard, for example, please take the code with you because it's full of regulation about the construction of the ship. Whereas the tank construction, as we discussed in the previous chapter, is a very important element, of course, as you hopefully did understood. All right, good. I will say mainly something about the international codes and regulations, and mainly about the gas code and the IGF code. It's a bit history built the gas code, because from the gas code there are different versions still active at this moment, and the first one is what we call the existing ships code. Maybe outdated. I don't expect that there are still gas carriers sailing which have been delivered before the 31st of December of 1976. I don't think so, although it is possible. But if there is still one sailing around, well, that one has been built and must be maintained according to these requirements. This existing ships code has been replaced by the GC code, where ships constructed between the 31st of December 76 and the 1st of July 86 were built according to this GC code. Most important one, and most of the ships are built according to this code. The IGC code is the international code for the construction and equipment of ships carrying liquefied gas in bulk. That is for all ships with the keel has been led on or after the 1st of July 1986. And where this revised IGC code, that means that the IGC code, which I previously mentioned, has been revised and entered into force the 1st of January 2016. And that applies to gas carriers constructed on or after the 1st of July 2016. There have been a lot of revisions again. You see that during history, the regulations are adapted regularly. From 83 to 2016, that's 1716, that's 33 years, that's quite a lot. In these 33 years, a lot of changes has been made technical on technical field. And you will see that in the construction and in the equipment of ships, and especially gas tankers, the technological evolution goes much faster than the evolution of the legislation. Legislation is always behind the technical evolution. So new things are invented, and the way to implement them on board vessels is always through the administration. You ask, when you invent something, you ask the approval of the administration, classification societies, whether you can implement that new invention on board of your vessel. All the new tanks developed by GTT are, of course, in accordance to the code, to the legislation, but they are more than that. They are far better than what legislation is requiring. So every 33 years, a new IGC code or a new gas code, too slow. But okay, we know that the IMO is not the fastest institute on earth. What has been changed in the revised IGC? Well, there's a lot of revision that has been done. I don't want to go through all this because the main part, the main elements are related to the construction of the ship. And as I mentioned, I don't want to go into these details. That is far beyond the scope of this course. Okay, just to read it, that's all. You don't need to know that. Everything which is important that has been changed will come later in the course. I introduced it later on then. Okay, beside the IGC code, there is, of course, since 2017, the IGF code, the Code on Safety for Gas-Fueled Ships. There is not too much about training in this code. So for me, if you know the IGC code, I'm quite sure that you also know the IGF code. I mean, that you know how to handle gas in a safe way. We have proven in the past that when you act according to the IGC code, that you do it on a safe way. And that is how I personally look to the IGF code. That if you know the IGC code, you definitely know also how to safely handle gas, and according also to the IGF legislation. Okay. According to the legislation, when your ship has been built and equipped according to one of the gas codes, depending on the date your ship has been built, you will receive a certificate of fitness indicating that your ship has been built and equipped according to one of the codes. For that, you need a periodic re-inspection during the lifetime. You will have an initial survey where you will have that certificate of fitness, and that certificate of fitness will also mention which cargoes that ship is able to transport. So the name of the gases are mentioned specifically. Then you'll have periodic surveys every 5 years, intermediate surveys with an interval of 30 months, and then the random inspection, just to make sure that your ship remains equipped and built according to the requirements of the legislation of the code which is applicable to your vessel. Also note that the gas codes are part of the provisions of Chapter 7 of the SOLAS. So in fact, you should see the gas codes as part of SOLAS Convention. And also Annex 2 of MARPOL is applicable to gas tankers. Other convention and regulation also like SOLAS and STCWV, of course. Good, let's have a look to the gas code. Some general rules for gas tankers which are important to know. The first one is that it is not allowed to have a cargo pump room on gas carriers. You all know how a VLCC is constructed. You know the presence there of a pump room containing all the oil pumps situated completely aft, just in front of the engine room. Well, here on board of a gas tanker, a pump room is not allowed. Between us, one of the major problems of a VLCC, yes, is the pump room, safety-wise. Therefore, on board of a gas carrier, cargo pump room is not allowed. That means that the cargo pump must be situated inside the tank. So in each tank, you'll have at least one pump. Second, no pipework is permissible beneath the deck level. A very important one. As I mentioned in one of the first presentations, every connection with the tank must be made on the tank dome. That means on deck. Well, the pipes must remain on deck. It is not allowed to have one single pipe below the deck level. Everything must be on deck, which is quite normal. Imagine you have a leak, well, the gas can escape in the atmosphere and is not blocked inside a compartment somewhere where it would only increase in concentration and finally create a possible flammable mixture. Everything which is on deck is in the fresh air and can be released in the atmosphere without further danger. So therefore, no pipework beneath the deck. These are two very important general regulations for gas carriers. That means that we have depot pumps, so pumps situated inside the tank. We have the cargo tank dome, which is the connection between the pipework on deck and the tank. We have compressor house on deck, which is the compartment that contains the cooling installation. And we have an electric motor room, which is a separate compartment close to the compressor room, which contains the electric motors that drive the compressors. Cargo tanks cannot be used for ballast purposes. If ever you had doubts about that, I don't think so, but this is just a confirmation that you cannot use any cargo tank for ballast purposes. Please note also that on board of a gas tanker, the cargo tanks are extremely clean, that the steel is all from is all stainless steel, and that it's quite shiny. Yeah, so it is not allowed, and it's not a good idea to put seawater inside because that might damage the steel, although it's stainless steel. Ship types according to the gas code, and according to the gas code, ships are subdivided in types related to what is called protective location. That means that the tanks are so placed inside the ship that they have a different protective location. Type 1G ships, there the tanks are so located that they are very, very well protected against any possible danger from outside. In 2G, you have significant preventive measures for protection from outside, while in 3G you have moderate preventive measures. So, according to the code, you have three types of ships, sorry. Type 1G, 2G, and 3G, but they're all related to the protective location of the tank. There is one additional type, 2PG, that's only for pressurized tank for a gas carrier of maximum 150 meters with independent type D tanks. This is for most of the time for inland vessels. That means that in these type 1G carriers, you will be allowed to carry the most hazardous products, while in 2G, 2PG, some less hazardous, and in 3G, non-hazardous products. 1G should survive to the most severe standard of damage like collision and stranding. This is what is meant by protective location. We will stipulate minimal distances between the tank, primary barrier, and the outer hull. So this is an extract of the IG code. It's just an example. Don't start studying these distances. You should be able to explain this, but not to know the distances by heart. That's not my intention. But you should know what is meant by protective location. So in this example, this is an example for the type 1G from the IGC code. And it says that the distance between the primary barrier and the outer hull should be at least the width over 5 or 11.5 meter, whichever is less. So if you have a ship of, let's say, 60 meters, then you should have a minimal distance of 11.5 meter between the primary barrier and the outer hull. 11.5 meter, that is huge. That's huge. Look now, 11.5 meters far away from where you're sitting now. That's a huge distance, 11.5 meter. That is the protective distance of this tank. So if there is an intrusion of an exocet or of another vessel, because they were sleeping at a bridge, you have a collision, well then that tank is protected by this 11.5 meter distance. The chance that due to this collision or stranding or whatever, the tank is damaged is for the type 1G tanks minimal. For the stranding, the protection is 2 meters of the width or the width over 15, for example. If you look to 2G to PG, the distances have been reduced to 76 centimeters only on the side. So here, the chance that after a collision the tank is damaged, yeah, that has arisen quite significantly. While for the stranding, the same requirements remain. Attention, in the new code, the 76 is replaced by 0.8 meters to 2 meters, depending on the volume of the tank. So in the new code, the requirements are more severe than for the IGC code. But again, don't study these distances by heart. But know the principle. The protective location of the tanks will define your tank, your IMO tank type. Chapter 19 of the code gives a summary of the requirements for each product. So as I mentioned in a few slides ago, you will have a certificate of fitness that will stipulate which cargoes you may carry. Well, if you want further detail on these cargoes when you need to load them, please consult Chapter 19 of the code. For an operator, Chapter 19 is a very important chapter of the code, maybe the most important one even. And it is a chapter which includes nothing else than tables like this example, where you will find in the first column, alphabetically, the name of the product. So let's take a dirty one, butadiene, for example. Butadiene, the UN number is 1010. You can ship it in a 2G, 2PG. So if your ship has been constructed according to the requirements for 2G vessel, on your certificate of fitness will be mentioned butadiene. Is an independent tank type C required? No. So that means that membrane tanks, type A tanks are allowed. Type B tanks, whatever. Is the control of the vapor space within cargo tanks required? No. That means that the cargo vapors will fill up the vapor space. Is there vapor detection required? Yes, that is required. Is because it's flammable. So you need a vapor detection for the flammability of butadiene. Some products is mentioned the T for the toxicity of the product. Gorging, you need a restricted gorging. This is so old-fashioned because a sea is closed gauging, and all gas tankers these days have a closed gauging, of course. But the code says that restricted gauging is sufficient. Medical first aid guide table number 310. And then in the last column, you will find references to paragraphs with additional special requirements for this specific product. So that means if ever in your life you will load or they will ask you to load butadiene, please consult chapter 19 of the IGC code or whatever code is applicable to your vessel. And then you go to the last column, the special requirements, and then you find a reference to chapter 17, paragraph 2, subparagraph 2, and you read that because that will be an additional requirement before you can load butadiene, and has to do, of course, with the specific characteristics of butadiene. Let's go a few lines lower to chlorine. UN number 1017, ship type 1G. If you have a product which must be transported in 1G, chlorine is extremely toxic. That is why in column D is mentioned independent tank type C required. Yes, because it is not allowed to have chlorine coming outside the tank to a line going through a cooling installation, for example. No, you can only transport chlorine in type C tanks. You load it, you close the tank, and it remains closed until you discharge it. You should fill up the atmosphere with dry air or with dry nitrogen. That is not really specified, but it's not flammable, so it might be air maybe. It's not mentioned that it should be inert. The vapor detection should be regulated for toxicity, and the gauging should be completely saved. Medical first aid guides, page table number 740, and special requirements, chapter 14 and 17. So please don't forget to mention that every time you load a different cargo, that you know these special requirements. Very important for the operator. Ship arrangements, the gas dangerous spaces, and the gas hazardous spaces in the new code. So a ship is subdivided by the gas code in gas dangerous spaces and gas safe spaces. These are the gas dangerous spaces: the compressor room, the hold space, the tanks and the piping, the spaces in the cargo area, which are not equipped to ensure that the atmosphere is safe at all times, and enclosed spaces outside of cargo area. Open deck zone, within 3 meters of any cargo tank. Open deck over cargo areas up to 2.4 meters above the weather deck. Compartment for cargo hoses, enclosed or semi-enclosed space having direct opening to any gas dangerous zone or space. Summarized in this figure. So everything which is cargo tank and the space around it, everything which is deck up to a height of 2.4 meters, and everything which is around vent mast and so on here in blue is considered as being a gas dangerous space. The red and the blue. What is green? The rest then is considered as a gas safe space. Forepeak, accommodation, engine room. Notice that here the first 3 meters after the facing are considered as gas dangerous. dangerous space. Are considered as dangerous space. There is something wrong with my cat. I don't know what. So excuse me for that. I'll try to continue. Um, so this is considered as a gas danger space. That is the reason why on these first 3 meters here of the accommodation, you will not find any opening in the accommodation, and the first door will only be after these first 3 meters. You have another gas safe space here, and that is the cargo control room on board of this gas carrier, which is situated there. Now more and more cargo control room is inside the accommodation. A gas safe space is then a space other than a gas danger space. Then these windows facing the cargo area are always fixed, closed. So you have the view forward, but you will not be able to open the window of your cabin. And all air intake should be equipped with closing device. You must be able to close every air intake for moments when you start gas freeing or so. Good. Ship arrangements for the protection of the electric motor room. As I mentioned, I pick some items from the code, from here to there, from the code, elements that are important for the operator. This is a very extremely important one. So we have the compressor room where the cooling installation is situated. That is this room. And you have here the compressors for the cooling. Yeah? These compressors are connected with a shaft to an electric motor, but this electric motor cannot be in the compressor room. Why not? Because the compressor room is considered as a gas danger zone. There are so many connections there that it might be that there is a leak. That is possible. Therefore, compressor room is considered a gas danger zone. You cannot put an electric motor in that room if there is a possibility to have a leak. So therefore, we have a separate room, separate space, namely the electric motor room, which is a gas safe space. How can we arrange things that this is a gas safe space? Well, by creating an air lock. Gas safe spaces will be kept under overpressure, while gas danger spaces will be kept under pressure. What is an airlock? An airlock is nothing else than a lock with 2 doors, where one of both doors is always closed. So it's the goal is that both doors remain closed, but if they must be open because you need to enter the electric motor room, for example, well, then you will open them only one by one. Here is an overpressure, and you don't want to lose that overpressure, and that is the reason why there is a double air system, a double closing system. Sorry. So if you arrive from here and you want to enter the electric motor room, you first check the visual indication. That's a simple red lamp here on top of the door. You check if that is illuminated, yes or no. If that is illuminated, that means that the other door is open, that someone is coming from the electric motor room into the airlock. If it's not illuminated, you can open the door, you can enter the airlock, close the door again, and continue your trip to the electric motor room. If you open the 2 doors at the same time, you have something like 5-10 seconds to close one of the doors, because otherwise you will lose the pressure of the electric motor room and you get a low pressure alarm of the electric motor room, and the ventilation will stop, the motors will stop, and everything here around will stop. Emergency shutdown. But that is not the goal, of course. The goal is to keep a permanent overpressure in the electric motor, the positive pressure type. When this positive pressure is lost, or there is a problem with the ventilation, for example, it will stop the motors automatically. This I told you already. I told you also already. Beside that positive pressure in the gas safe space and the negative pressure in the gas danger spaces, we also have to take account of the density of the vapors from the cargo we are transporting related to ventilation systems. For example, in the compressor room, we are looking for a negative pressure inside the compressor room. That means the fan is situated at the outlet. We are sucking air out of the compressor room and sending it in the atmosphere. The inlet is passive. In this case, as the valves are situated here, we have entrance of air coming in at the top, going to the bottom, and then leaving the compressor room by this shaft and to the ventilator and then outside. That means we are ventilating by displacement method. In the gas trade, we will always use change of atmosphere. We will always use the displacement method. We will use the fact that vapor of gases in general is lighter or heavier than air. There is an important difference in density between the density of the vapors from the cargo and the density of the air. So, in this case, the valves are set for a gas which is heavier than air. Because what will happen when there is a leak in the compressor room? Vapor will escape. The vapor is heavier than air, so it will accumulate here at the floor. This is a very dangerous situation because that is where we will operate. Therefore, we have immediately evacuation of the vapors at the bottom. The suction of the ventilation is situated at the bottom of the compressor room. Same thing here. This is top in, bottom out. This is an example for when we transport LPG. The vapors of LPG are heavier than air, so then the valves should be regulated like they are here in this drawing. If, for example, we change cargo and we take ammonia vapors are lighter than air, then vapors should be evacuated at the top of the compressor room. So then this valve must be open, that one closed, so that the inlet is coming in from the bottom towards the top and out. So it is not only a question, ventilation on board of tankers, it is not only a question of under pressure and overpressure, but also a question of top in, bottom out, or top out, bottom in. Of course, all equipment used in hazardous areas must be intrinsically safe. That means that the energy released is insufficient to provide an ignition for a flammable mixture. About national codes and regulations, because that was the most important elements which I found from the international codes. I will not go further into detail. It's quite boring stuff, but these, of course, are for me important for an from point of view of an operator. For national codes and regulations, I will not go into detail because they are so different, and so I leave it for this chapter. I leave it up to here. Thank you very much for your attention and hope to see you next time.